From Swagman Media, this is the Jolly Swagman podcast. Here are your hosts, Angus and Joe.
Hey, ladies and gentlemen, welcome back to the show. It's great to be with you. I'm Joe Walker, and this week my guest is Leonard Susskind. Leonard is one of the preeminent theoretical physicists in the world and is widely regarded as the father of string theory, a possible theory of everything. I met Leonard at Bites Cafe on Stanford University campus, and we smashed some blueberry scones before going up to his office to record this conversation. And Leonard told me that he doesn't do many interviews with non-physicists. He finds them frustrating because usually the premises of the interviewer's questions are wrong. But after we finished recording, he said this wasn't one of those conversations. So needless to say, I left Stanford campus with a certain spring in my step. But listening back to this conversation, I still get chills. It was truly extraordinary, and you'll soon hear why. So I spoke to Leonard about his life in physics, how he first found his way into the discipline. I spoke with him about his friend Richard Feynman, the great physicist of the 20th century, who had a huge impact on Leonard's career. I spoke with him about his famous black hole war with Stephen Hawking, which Leonard ultimately won, no spoilers there, and about the application of the holographic principle, which Leonard helped come up with, to the universe as a whole. We also spoke about string theory and what it means for the concept of the multiverse. So this conversation covered everything from Leonard's career through to some of his most famous ideas, and I decided to leave it relatively raw and unedited. You'll hear a few times me asking Leonard to hold the microphone closer to his mouth. You'll hear some Stanford physics students interrupt us, but above all, you'll hear the story of one of the world's greatest living physicists, Leonard Susskind. So, without much further ado, please enjoy this conversation. And we are on. Leonard Susskind, thanks for joining me.
Good morning.
It's great to be with you. I've been following your works online for a long time. Can't say much of the mathematics has remained with me, but you're certainly someone who has this great ability to translate complex physics to a lay audience, I guess.
Yeah, it's fun. I enjoy it. I always learn something from trying to figure out how to explain something to maybe what's a layman? Yeah, lay people.
Yeah.
It's very enlightening to try to understand a thing at a level that can be understood outside the immediate framework of my colleagues.
Yes, absolutely. We're going to talk about some ideas that you're well known for in a bit, but first I just want to introduce you to the listeners. And you were born...
Hi, listeners.
Hey, everyone. So you were born in New York to a Jewish family.
I was.
And so I've spent a lot of time in Manhattan, but I've only ever run through the Bronx. And I don't mean that disparagingly. I was literally there for a running race.
Okay.
Yes, but describe what it was like there back in was it the 40s you were growing up there?
Yeah, 40s and 50s. What was it like? It was very different than it is now, perhaps much less interesting. But the part of the Bronx that I came from was sort of ethnically almost all white, but diverse anyway. There were Italian neighborhoods, there were Irish neighborhoods, there were some Jewish neighborhoods. I did not come from a Jewish neighborhood. I came from an almost completely Irish Catholic and Italian Catholic neighborhood. So I always felt a little bit like an outsider. I remember when I was a little kid, we were sitting in front of our house, and our apartment building, and it was immediately across from St. Helena's Church, a great big church. And every day, I was 4 years old. Every day, the priest would walk by, and all the kids that I knew would say, "Hello, Father. Hello, Father. Hello, Father." And I was wondering, I knew these kids' fathers. How did this man have so many kids? But I was a bit of an outsider.
And your family was in the plumbing business, is that
My
right?
family was in the plumbing business, right? Right. My
So
father was a plumber.
He was a plumber, yeah. And tell me the story of the time that you told him you wouldn't be following him into the business.
Yeah, I went to college, CCNY, City College, which is a free college in New York. And the whole point of going to college was that my father wanted to go into the business of heating engineering. Heating engineering meant replacing all the furnaces and boilers in the tenement buildings in New York. And he didn't know enough about heat. He just didn't know enough about the engineering and the mechanics of heat. He didn't know what a BTU was. BTU means a British thermal unit. And people kept quoting properties of furnaces and boilers in terms of BTUs, and he didn't know what a BTU was. So he told me I should go to college to find out what a BTU is. And that's what I did. I started college in engineering school, but after about a year or so, 2 years, more like 2 years, I realized engineering was not what I wanted to do. I'd taken a couple of physics classes, and I really got excited about it. I wanted to do physics. So at some point, I had to tell my father I wasn't going to be a plumber. I wasn't going to go into the heating engineering business with him. And so I was married. I had a kid. We went over to my father's house, and my father, he was a tough guy. He was, he had hands like a vice. He could squeeze walnuts and break them with one hand. And he was standing in front of one of our pieces of machinery, the pipe cutting machinery, cutting pipe for the next day's work. And I said to him, Benny, I called him Benny, I don't think I'm going to be a plumber. I don't think that's what I want to do. And he looked at me, with, almost fierce fire in his eye. And he said, what do you mean you're not going to be a plumber? Or maybe I said engineer. I don't know. But I'm not going to be an engineer. He said, what do you mean you're not going to be an engineer? What are you going to be? A ballet dancer? And I said, no, I'm not a ballet dancer. I'm going to be a physicist. And his reaction was very, very funny. I mean, it's hilarious in retrospect. He said, no, you're not going to work in a drugstore. A drugstore, I don't know if in Australia you use the same term, a pharmacist?
Yeah.
Pharmacist. He thought I meant pharmacist. He said, no, you're not going to work in a drugstore. And I said, no, Benny, I don't want to be a pharmacist. I want to be a physicist. And he said, what's a physicist? What the hell is a physicist? And we sort of skirted around it a few times. And then I said the magic word which just opened up the whole world for me. I said, a physicist like Einstein. Einstein? Einstein. He knew Einstein. Every Jew in the whole world knew who Einstein was.
Of course.
In fact, everybody altogether knew who Einstein was. And he said, you any good at this? And I said, yes, I think I'm very good at it. He thought for a little bit, and then he said, okay, you're going to be Einstein. Okay, that was good. But then my mother came in with my wife and my baby, and she was hysterical. She was convinced that we were going to starve. She was convinced that I wouldn't make any money, that we'd all starve. And she was crying about it. My father took a look at her and he just said, he was always very kind to my mother, but this time he just turned around, the fire in his eye, and he said, shut up, he's going to be Einstein. And that was the end of the story. That was it. I was then free to become a physicist.
Two things strike me about that story. Firstly, that's a lot of pressure on a young man.
Yeah,
and
it was frightening.
And secondly, it's incredible how much belief your father had in you.
Yeah, that's right. He did. Even though in many ways I was what you call a ne'er-do-well, I had caused plenty of trouble, been in trouble at various times, I always had incredible support from my father. Yeah. Anything I wanted to do was always the right thing.
Yeah. Did you ever meet Einstein?
No. I was 15 when he died. And I remember the day that he died, or at least I remember the day it showed up in the newspaper. I was walking home from school. There was a newsstand, and on the newsstand, big headline, Einstein dies. And although I had no idea of physics, I didn't know what Einstein did, it really touched me. Thing touched me very deeply. And so I was 15 at the time, 15, 14, about then.
So, from that moment when you tell your father that you're going to be Einstein.
No, I didn't tell him I was going to be Einstein.
I'm joking. But
he told me.
So the rest is history, and you've been teaching at Stanford now, I think we were just discussing, for 40 years?
40 years,
40 years.
1978. 78, 90, 2008. Yeah. Right.
Wow. And one person who I think it's fair to say...
I was a professor when I came here. I had already been a professor for 10 years. So.
Of course, yeah. And one person who had a particularly strong influence on you personally and professionally was the great physicist of the 20th century, Richard Feynman,
yes.
who was a Nobel Prize-winning physicist. Can you firstly just describe Feynman, the man, to us?
Yeah, Feynman was what you might call a man of many parts. He had he had a most unusual personality. He was a clown. He was a performer. He was a bongo drummer. He was a lover. He was everything you can think of that makes people interesting. And he was probably one of the 2 or 3 great theoretical physicists of the 20th century. So, and he loved to perform. And one of the kind of performances he loved was to show somebody how easy a thing could be, how easy a physics problem could be when that other person, and the other person could have also been a great physicist, had made a calculation which was very difficult, very complicated, and Feynman would stand up and show you how to do it in 5 seconds. He loved that.
But it was a party trick.
It was a party trick on the one hand, but it also represented the way the man thought about physics. Always simply, always with the easiest possible way to think about something, always with a way to think about it that could be explained easily, almost to a layperson. His Feynman diagrams, for example, were an example. And there was this funny mix of performer and great scientist, which was almost unique.
There's a great book which I'd recommend to listeners. Surely You're Joking, Mr. Feynman.
Surely You're Joking.
Yeah.
Most of that book was had to do with things that took place before I knew him.
Right.
He was 20 years older than I am.
Yeah.
Than I was. Yeah.
There was a sense in which he would almost go out of his way to generate these anecdotes about himself.
Yeah. As far as I know, all of the anecdotes, they may have been embellished a little bit. He had a lot of fun talking about them and things. But as far as I know, they were all true. Mm-hmm. They all represented what had really happened. Mm-hmm. I don't think he made stuff up. But he loved being the center of attention. On the other hand, there was something else about him. He liked a situation where, a competitive situation, who could be cleverer? And he almost always came out on top. And he loved it, and people sometimes felt resentful. But what I found out about him, we were close enough, and we had done this enough times that some of the games I had won. And he loved it just as much when I won as when he did. So there was room in his personality for other people to also be performers. I admired him probably beyond anybody else, but I also realized that there was a certain aspect to his personality which you could almost call clownish. Mm-hmm. Clownish in a good sense, a performer. And anyway, Richard was Dick was a very important formative influence on me.
Yeah. So he was about 20 years your senior.
Yeah, I think 21.
21. Did it feel like a mentor-mentee relationship, or was it more friends and equals?
Both.
Okay.
Well, as far as being a mentor, that mostly took place in my own mind before I actually knew him. I admired the way he did physics. I admired the way he explained physics, and I sort of tried to emulate it to some extent. Not to imitate him, but to try to think simply. So to the extent that he was a mentor, it took place before I even knew him.
Right.
On the other hand, by the time I knew him, he was already 56 years old. I was 36. We became friends. Friends and I wouldn't say colleagues, just friends, yeah.
I've got a couple more Feynman questions before we move on. So earlier we were talking about how strong your relationship with your father was, and Dick had this theory about fathers in physics.
Yes.
Can you tell us that story?
Yeah. He had a similar relation with his father, that is close, not only close, but his father had taught him all sorts of things, and I had the same relationship. Feynman had asked me about my relationship with my father. Was I close to my father or close to my mother? And I said, well, I was close to my father. I had most of my interaction with my parents, intellectual interaction or whatever, learning, came from my father. I was much closer to him. And he said, yeah, he had exactly the same experience, and he had become convinced that to be a really good physicist, that you had to have that kind of relationship with your father. And he decided to try to explore it. He decided to try to confirm it. So he went around and asked all his friends who were good physicists whether they had close relations with their father or their mother. And he was thunderstruck to find out that they almost all had the strongest relation with their mothers. I was the first one that had the same experience that he did. So that was, it was an amusing story.
Yeah. Well, I wonder why he thought that in the first instance. What was his theory?
Well, it's the way he got interested in the way the world works, through his father.
Okay.
Through his own experience.
Yeah.
And I might have said the same thing. Had you asked me, I might have said the same thing, that understanding how the physical world works often comes from fathers, I would have said. Yeah. I'm not. I like him. I'm no longer sure it was true. I think it's not true.
So next week will be, if Dick was still alive, his 100th birthday.
That's right.
And you're going down to Caltech. They're putting on a celebration, I suppose.
That's right.
And you've got to speak.
I will.
And another time you had to do quite a significant speech about Dick was on the TED stage.
That's right.
And not everyone's familiar with this, but TED has incredibly rigorous pre-screening protocol where they make you rehearse the speech. You have to present it first, I think, online, over Skype or something. Then you actually physically rehearse it on the stage, and they give you feedback. Was your experience similar?
No, but only because I refused to rehearse. My experience with rehearsing is disastrous, has been disastrous. Whenever I try to prepare in that way, I always find that when I'm actually speaking, I try to remember what I said when I rehearsed, and that's deadly. That's not a good way for me to present to a public. Mm-hmm. I have to do it fresh. I have to do it with no preparation. I have to just start talking. And so I told them I would not rehearse. And they said, you have to rehearse. And I said, well, I will not rehearse. And they said, okay.
Yeah.
So I didn't rehearse. Perhaps I'm the only TED speaker who never rehearsed.
Oh, that's so good. So we're going to talk about some physics now. And
I had an advantage, you see.
Oh, yeah.
I had an advantage. This was about Feynman. And I am probably one of the last physicists who was personally close to Feynman, so they had no choice but to...
You had the bargaining power.
I had the bargaining power. Right.
That's where the New York upbringing comes in strong. Right. Okay, so Leonard, let's talk about some physics. And your ideas are absolutely fascinating. The first one I want to talk about is the famous black hole wars with Stephen Hawking. Yeah. And we're not going to turn this into the Leonard Susskind and Stephen Hawking show.
No, please.
But it's a very, I guess, entertaining tale. And let's begin firstly with the time that you first met Stephen. It was San Francisco in 1981, and you were at, I believe, Werner Erhard's house.
That's right. Yeah, Werner Erhard was a famous man around San Francisco. He was a salesman. He was a guru. He had a cult following, but he also himself was a kind of wannabe physicist. He loved physics, and so he would bring to his mansion, a very fancy mansion in San Francisco, groups of physicists for meetings. This was one of these, and I cannot really remember who was there that time, other than 4 people that I remember very distinctly, apart from Werner. That was myself, I remember. I do remember myself pretty well. There was Stephen Hawking. There was Gerard Hooft. Now, I think I've said that as well as I can say it, but most Americans would say Gerard it Hooft. Actually, they would say Gerard to Hooft, but that's wrong. He's a Nobel Prize winner, very famous physicist. And the other person I'll tell you in a moment, Stephen had presented his ideas about black holes, and in particular, why black holes violated one of the sacred principles of physics, the so-called information conservation. Very deep principle of physics that nothing ever really gets lost. Even if you burn up a book, all of the information that was in the book, in principle, could be reconstructed from the smoke and fire and that it emits. Information can't be lost. And Stephen made this very, very compelling argument that when stuff falls into the black hole, and when the black hole evaporates, which it does, everything would have to be lost. And that really rankled. It violated certainly my most deepest beliefs about the way physics works, and it also violated the way Gerard it Hooft thought physics worked. And I do remember that after Stephen's presentation, both Gerard and myself were completely confused. We couldn't see what was wrong with what he was saying. And the three of us were at the blackboard, Stephen in his wheelchair, Gerard and myself at the blackboard. And I remember distinctly the most concentrated, fierce look on Gerard's face, trying so hard to undermine what Stephen was saying. And Stephen sitting there with a smile on his face as if to say, I'm right and you're wrong and you're gonna admit it one day. And I was, of course, on Gerard's side, but also unable to see what was wrong with what he was saying. And there was a 4th person with us. The 4th person was a young physicist by the name of Martin Roczek. Martin was not yet a famous physicist himself, although he did become one. He was one, I think, of Stephen's students or one of his young people around him. And whenever Stephen traveled in those days, he still was able to speak, but you could not understand what he said. There was a kind of mumble, a kind of grunts and groans because of his physical ailment. But if you stayed around him long enough, you could learn to understand what he said. So he always traveled with a young physicist, a different young physicist, but always had one with him that was able to understand him and would use him as a translator. So at one point, while Gerard was fiercely looking at the blackboard, I was struggling to try to make sense of what Stephen said. Stephen said something and couldn't understand it. So I asked Martin, will you explain to Stephen, this is what I think, and please try to explain to me what he said. Now, explain meant not just to say the words, but to explain the physics, because Martin was a good physicist. Martin just looked like he was a deer in the headlights. He just looked at me and said, I have no idea what Stephen said. I concentrate so hard on trying to understand what he's saying, to translate what he's saying, that I can't even begin to understand what the content is. So it was very, very hard to interact with Stephen. It got harder as the years went on, and so I considered myself a friend of Stephen's, but to say a friend usually means that you can communicate with somebody. And Stephen was very hard to communicate with, not because he was a difficult person, but because he had this difficult condition. So,
let's talk about the principle of micro-reversibility, which you alluded to. So you mentioned that if you burnt a book, it would turn to ashes, but the information would still be there. And to a listener who's not familiar with quantum mechanics, that might sound paradoxical because all the lines of the book and the story are destroyed. But you mean something slightly different. Can you just explain that?
Well, first of all, if you destroyed the book, I mean, let's say burn the book, or something equivalent, in an isolated environment where there's nothing else around to interact with it, in a vacuum, let's say, then what comes out is a bunch of smoke and dust and light and other things. And imagine that you could capture all of that. If you could capture all the stuff that came back and then examine it with infinite care and with infinite precision, in principle, you could reverse it. You could imagine running it backward, just like a movie being running backward, and reproducing what it was that originally was, or the original properties, all of the original properties of that book. In principle, it'd be very difficult. If you make a little mistake, it all goes down the drain. But in principle, physics is reversible, which means you can run it backward, like running a movie backward. You might have taken a movie of the book burning, and you will run it backward. You start with smoke and gas, and you run it backward, and all of a sudden it reassembles itself into a book. Well, physics is like that. In principle, that's possible. What Stephen was saying was that when a black hole forms and evaporates, the stuff that comes out cannot be reassembled into what went in, just because a black hole is a black hole. And so this idea of micro-reversibility, that you can, in principle, know the past from the future. You can, in principle, reconstruct the past, no matter how complicated things got. You could reconstruct the past from what you now know or what you may know in the future. That was, as I said, a sort of sacred principle of physics. And Stephen was saying it's not true when there are black holes. This really rankled and bothered Tuft and myself. Also turned out to be wrong.
Yeah, that's right. No spoiler there. But describe what you and Tuft think happens when information moves beyond the event horizon of a black hole.
Okay, both of us were convinced.
You have to move your mic up.
Yeah, both of us were convinced that black holes are no different than other ordinary kinds of systems, that the information in whatever it was that fell into the black hole would be returned when the black hole evaporated. Black holes do evaporate. They evaporate. What comes out of them is light and heat and photons and other particles. And we were both convinced that that stuff which came out of the black hole, in principle, would allow you to reconstruct what fell in, this micro-reversibility idea. But to make sense out of that, it was necessary to think that, in a sense, that the black hole horizon, the place, well, whatever horizon is, the place where stuff gets lost behind, functioned as a kind of hologram, that kept track and recorded the details of everything that fell in. And this led to the idea that that a region of space is related to the boundary of that region of space in the same way that the hologram is related. The hologram is a strip of film, two-dimensional film, but it represents a whole three-dimensional reality. And in the same way that the strip of film is related to the three-dimensional reality that it represents. So this is a complicated idea, but it basically said that the world can be represented in terms of the things that happen at the boundary of the world, wherever the boundary is. In the case of the black hole, it would be the horizon of the black hole. In the case of our universe, it would be the outermost reaches of the region that we can see through the most powerful telescopes, that everything is encoded in a kind of hologram that represents the three-dimensional reality of what's inside that world. This is something that has now become an important pillar of physics, this idea of the holographic principle. And eventually it was what both 't Hooft and I came to the conclusion, that the world is a hologram. And that is, as I said, that is now.
So, I mean, the indestructibility of information is such a fundamental principle of physics. How do you account for Hawking's, refusal to accept that in the context of black holes?
First of all, let me say that although Stephen turned out to be wrong, his way of thinking and the question that he asked was so profound and so deep that it is dominating physics for the last 40 years.
Right.
It is completely dominating physics, unraveling what was wrong with what he said. Well, I don't know. It may be a psychological question. I don't know whether Stephen secretly may have thought maybe he was wrong. There's no way to know. I think he wanted to be right. Mm-hmm. He wanted his legacy to be, among other things, that quantum mechanics would break down for black holes. Instead, the legacy is going to be that quantum mechanics doesn't break down for black holes, but in order to escape from Stephen's paradox, you have to think in entirely new ways that people had not thought about before. So I can't answer why Stephen was resistant to the idea.
When was the moment that you and 't Hooft were declared?
't Hooft.
't Hooft, sorry.
It starts with an apostrophe.
Okay. Yeah, that's right. Okay,
't Hooft.
So let me practice that. 't Hooft.
Yeah, good.
So what was the moment when you and 't Hooft were declared winners of the black hole war?
Oh, I don't know. I mean,
did Hawking concede?
Yeah, I think he did.
Okay.
Yeah, I believe he did.
Yeah.
I don't remember what year. Yes, he did.
Okay.
But more important than that, the entire community of theoretical physicists, at least that part of which I think is the best part of it, agreed. Now, what was the point? The point was probably the point at which a physicist, a very great physicist, who fewer people have heard of than some of the other of us, his name is Juan Maldacena. Juan Maldacena is probably one of the really great physicists of our times. He was the one who really put a precise mathematical structure behind this idea of the world as a hologram. Maldacena, who is now at the Institute for Advanced Study, he is probably the preeminent theoretical physicist in the world. He really took this holographic idea very seriously and constructed a truly rigorous mathematical, precise version of it, where when physicists saw it, they said, yes, that has to be right.
Wow.
And so I think that was the turning point. That was Maldacena's work was 1998. It probably took a couple of years. A couple of years later, Edward Witten and I wrote a paper how this was connected with the holographic idea. And sometime over the course of understanding Maldacena's work, the tide shifted completely.
Edward Witten, the Harvard physicist.
No.
Princeton, yeah.
Institute for Advanced Study.
That's right. One of the smartest people in physics.
One of the smartest people in physics.
In the world, maybe.
There's different kinds of smart.
No, that's right. That's right. Let's talk about the holographic principle then. So when you say that the world is a hologram, obviously you mean the universe.
Yes.
What do you mean that it's a hologram?
What it means is that well, first of all, what is a hologram?
Yes. Yeah.
Okay.
Good question.
So a hologram is a two-dimensional piece of film which encodes a whole three-dimensional world. To reconstruct the three-dimensional world, you shine some light on this two-dimensional strip of film, and that light will produce an image which is a full three-dimensional. You can walk around it, you can look at it from all sides. You've seen holograms.
Yes.
So you know that the hologram has a full-fledged three-dimensionality to it that an ordinary photograph does not.
Sorry, I'll just have to hold it up. Yeah.
Yeah, an ordinary photograph does not have this property that you can walk around it and see what's behind somebody's head in the photograph. Holograms do have that feature. So but the important thing is not the shining of the light. It's the fact that the holographic piece of film, which is two-dimensional, really contains all the information about a three-dimensional world. That's remarkable when you think about it. Just a two-dimensional piece of film that if you do something to it, you can reconstruct the whole three-dimensional scene in front of you. That is what the holographic principle said about the real world. It said you can think of the real world as having a boundary very far away, which is two-dimensional, and encoded in everything that happens on that two-dimensional distant surface is the entire three-dimensional world inside that surface. So if you imagine drawing a big sphere around yourself, a great big huge shell around yourself and everything that's in your field of view, that the correct mathematical description of everything inside your world takes place in terms of things which are happening at this large, very, very distant shell. This was something totally unexpected.
Yeah. Wow.
Right. No, it's very unintuitive, but it's come largely through the work of Maldacena to become very much a standard pillar of physics today.
When you and Itolf discovered the holographic principle at the event horizon of a black hole,
Yes.
How did that then lead to the holographic principle applied to the universe as a whole?
Right. Well, both of us understood that the horizon of a black hole is just a boundary, is just a sort of arbitrary boundary that separates the outside from the inside, and I think both of us understood immediately that that could be applied more widely than just the surface of a black hole.
Right.
I made a technical argument about it, not a very mathematical argument, but a technical argument based on based on what? Based on Stephen's work that it had to apply to the whole world.
And this was a famous paper you wrote in 83 or 4?
Yeah, it was called The World as a Hologram. When was it?
It was in the 80s.
No. Well, it was 1993.
1993.
1993, okay. Yeah. 93, 94.
Well, I'm going to link to the paper because it's on
The
our
World as a Hologram?
website. Yeah.
At 94.
Yeah. 94.
94.
Yeah.
The ideas emerged from 93, and Itolf had a similar paper at about the same time, slightly earlier, and we had talked about it, and so we did have some interaction about it.
It's really a testament to how complex these ideas are, that from that first meeting with Hawking in 81 all the way through to the publication of the paper in 93, 94.
Right. 12 years.
12 years you're working on that problem.
Right. And it still took another 5 years before Maldacena really nailed it. I mean, when I say he nailed it, he produced a version of it, of this holographic idea, which was so mathematically consistent and compelling and rigorous that nobody who understood the issues could deny it.
I want to ask you about string theory now. I think this is probably, originally how I came across your name. I went to a talk that Brian Greene did in Sydney a few years ago, and that's when I first encountered string theory, and it was possible to become obsessed with something without actually understanding it.
Right.
That was me. You're widely regarded as one of the, the founding fathers of string theory.
Yeah, 1969, long time ago.
Wow, okay.
Before you were born, I suspect.
Oh, yes, absolutely. And so string theory is held up as a possible theory of everything.
Yeah.
I guess before we talk about string theory, can you just define this concept of quote-unquote theory of everything?
I didn't make up the term. I don't want to be responsible for it.
Oh, do you want me to define it then?
Yes, you define it.
Okay. So in physics, there are two grand theories. One is general relativity, which describes gravity, things at the large scale.
Yes.
And the other is quantum mechanics, which is
Indeed.
Leonard's specialty, which describes things at the microscopic scale, so particle physics. And one of the great challenges in physics is that these two different modes of analysis are mutually incompatible. So physicists have been searching for, I guess, the holy grail of physics, which is one theory of everything that can unify both general relativity and quantum mechanics. And I guess that's where string theory comes in.
Yes. What you say is right.
Okay.
But I don't think it's what the inventors of the term theory of everything meant at the time. What they meant was a theory of particle physics. They were thinking about the generalizations of the theory of electrons and protons and neutrons, which involved other particles called gluons and X bosons and Y bosons and Higgs bosons, and on and on and on. They were really thinking about the world of particle physics, which is a quantum mechanical world, to be sure, and ultimately it will involve gravity, but they were not thinking about those things. They were just thinking about particle physics, a theory that would describe all of the particles in nature. And so when one thought of string theory as a theory of everything, that really meant that string theory, some version of string theory, would be put forward, which would have electrons in it, photons in it, quarks, gluons, Higgs bosons, and all these things with exactly the right properties. That's what they were thinking about. My own, although I was probably responsible for one of the first papers on the ideas of string theory, I really thought that they were being overly optimistic, that string theory as we knew it at that time and even now was probably incapable of describing the world as we know it now. And I still think that's true. Mm-hmm. Perhaps some theory which is inspired by string theory and which is more general, very likely perhaps can describe all of the particles that we know in nature. But I think the way we understand it now, I suspect it's not capable of explaining everything about particles. Mm-hmm. Nevertheless, it is a theory which in its current form does contain quantum mechanics. It is a quantum mechanical theory, and it also has properties of gravity, the gravitational attraction between things and so forth. It has black holes. And so that means it's possible to analyze it and understand things about the connection between gravity and quantum mechanics, even though the real theory of the world may be a little bit different. And my guess is it is a little bit different.
Got it. So it's sort of like a recipe for understanding the world without going into sort of the chemistry of
That's exactly right.
Of baking.
That's exactly right.
Right.
That's exactly right.
So just describe it then, sort of colloquially to us. Yeah.
Sean. Okay. All right. Okay. Let's just keep going.
Okay. Do you want me to tell him? Do you want me to talk to him?
No.
Oh, it's all good? Okay.
Edward. Okay, they'll find some other place. Okay. They're afraid of me.
Oh, right. For good reason?
No.
No,
they're my friends.
Oh, okay. All right. So tell us what string theory says about the world.
Well, ordinary particle physics is based on something called quantum field theory, but it's a very simple, it's a very complex idea. I take it back. It's not a simple idea. But in one version of it, it just says that particles are point particles.
So like
little
dots.
tiny points, little dots which are so small that they have no extension at all. Of course, they can be combined together into many such dots. If you put a lot of quark dots together with some electron dots, you can make an atom and so forth. But the particles are fundamentally dots. That failed to explain originally the properties of protons and neutrons correctly. And one property that protons and neutrons have is they tend to behave like elastic strings. If you hit them, they vibrate. You can set them into rotation. These are things that points can't do. A point can't oscillate like a vibrating string. It can't rotate. A point can't rotate. It can't spin like a basketball that's set into spinning motion. Basketball has to have size in order to spin. So protons and neutrons and other particles experimentally were known not to be points. And the first versions of string theory were intended to describe those particles which did not behave like points. Known particles, particles that we see in the laboratory. So the first versions of string theory said you go one step up. Instead of saying a particle is a point, let's say it's sort of like a one-dimensional little curve, a string, and it vibrates like a rubber band. And that worked. It just worked very nicely to explain the properties of protons and neutrons. And that was the first version of string theory, the one that I was most involved with in 1969. Sometime later, a physicist named John Schwartz and a colleague of his, a French colleague, Joel Shirk, realized that the same kind of theory could be applied to a much smaller objects, namely gravitons, the things that have to do with gravity. And they put forward the idea that perhaps not just protons and neutrons, but all particles, including those which were responsible for gravity, as well as photons and electrons, all particles could be represented in this way as little vibrating strings. That was a very powerful idea because it answered some of the paradoxes, some of the inconsistencies between quantum mechanics and gravity, and became, in a sense, the leading theory of how gravity works. That took time. It took years. But even that was not enough to completely explain the properties of black holes. It did not explain the properties of black holes. So we're still wrestling with how to think about black holes properly. Does string theory describe them, or is it something even more primitive and fundamental than string theory? Are there some degrees of freedom, some objects which are even more fundamental than strings? Are strings made of something else? Are they themselves made up of a lot of little points? And the answer is we don't know. Mm-hmm. But black holes are the root to understanding this connection.
Wow. So string theory says that the most fundamental particles are these little loops, and
the most fundamental, yes.
Sorry, that's kind of an oxymoron.
Well, yeah. That was thought to be the case, and it may be the case, but it was not completely sufficient to understand the properties of black holes. In black holes, these little strings seem to sort of melt and disintegrate into something which may possibly be more fundamental than the strings.
Wow.
Bits of information, themselves perhaps more fundamental than the strings, and we don't know. We're exploring that. Lots of ideas, much of which is mathematical, and that's where we are now.
The vibration of these little loops produces different types of particles.
The vibrations produce different types of particles.
Right, so vibrating in one way might create a proton.
Something like that.
Okay.
Yeah.
So the universe
slightly simplified, but not
what are you talking about? That's string theory.
Yes. Let me just say yes.
And so the universe is just this symphony of all these vibrations.
Something like that. Right. A very poetic way to put it.
Yes. I love a good metaphor for understanding science.
Right.
Okay, well, that's incredible. And string theory has helped us to understand the idea of the multiverse, which I kind of want to finish on this. How many universes are there?
How many? Don't know.
But we no longer believe. Well, I mean, consensus no longer says that there's just this one universe that we're in.
there's certainly consensus doesn't say that, but it's also probably correct to say that there is no consensus.
Yes. Yeah.
Right. So here's what we know. Here's what we know from observation of the world. We know that the universe is much bigger than the portion we can see. You could ask about the surface, about the Earth. How did Columbus know that the Earth was much bigger than the region that he was able to see with his eyeball when he looked out on the ocean? The thing that told him that the Earth was much bigger than the region he can see is how flat it appeared. It appears very flat, the ocean, and therefore the ocean must be very big. If the ocean was as small as a pinhead, it wouldn't look very flat. It would look like a tiny sphere. If the ocean was no more than 3 miles big, you would look out and you would see the curvature of the Earth would be very distinct. The fact that the Earth looks so flat told Columbus that it must be very big. Okay, I don't know what Columbus actually thought, but in any case, we see the same thing. We see a very flat universe, three-dimensionally flat instead of two-dimensionally flat, but we see a very flat universe through telescopes and so forth, and that tells us it must be very big. But just like Columbus, whose observations were bounded by the horizon, our observations are also bounded, and so we can't see all of that universe. Most of it is out beyond our telescope. So we know it's very, very big, much more than we can see. And so for all we know, it could be very different out at very, very distant scales. That's one thing, the size of the universe. The other thing does come from string theory, and it's the fact that string theory produces many, many, many different kinds of environments, very many different kinds of solutions to, for example, what the particle physics is like, what things are like. And putting these things together just suggests that the universe is very varied from one place to another. One place it's described by this kind of string theory, another place it's described by that kind of string theory, on vast, vast scales. The equations seem to say that. The equations seem to say that the universe is not only very large, but very diverse in various places. That raises the question, what is it that determined what kind of world we live in? And the answer could just be that almost all these different kinds of environments are unsuitable for life to exist. Where do we live? Perhaps the answer is we live in the kind of places where life is possible. And that would answer a lot of questions about why our universe seems so fine-tuned for our own existence.
So this is what we call the anthropic principle.
This is what we call the anthropic principle, but it's not that crazy. It just, if you ask the question, the universe, even the part that we can see, even just the solar system is pretty big. The part of it that's occupied by planets is a tiny, tiny fraction of the volume of the solar system. By what accident of fate do we happen to live on a planet? Well, the answer is you can't live off a planet. That's all. It's just life can't exist without without oxygen, without the things that planets provide. Why do we live on an Earth-like planet? Well, the other planets are just too cold. The other planets are just too hot. The other planets don't have a suitable ocean or whatever, though where life might have formed. So why do we live on the Earth? We live on the Earth because the Earth is one of the few places in the solar system where life can form. The logic is exactly the same. It's not deeply philosophical and full of mysticism or anything else. If the universe is very big and very diverse and contains many, many places where life cannot exist, then we will simply wind up being in the kind of place where it can exist.
It's actually such an elegant, mind-blowing
It's an elegant, that's right. Is it correct? Work in progress. Work in progress. It's controversial. Most physicists didn't want that to be the answer. They wanted the answer to be that there would be a unique theory which, when you solved it, would explain exactly the properties of the universe we live in, and that it would not be contingent on particular kinds of environments. It would not be like the Earth, which has a certain set of properties which are sort of accidental, but it would be some unique solution of some equations. That's exactly the opposite of what the anthropic principle says. The anthropic principle says the universe is wildly varied from place to place over very large distances. And where do we live? We live in the kind of place where life is possible, period.
So cool. So, I mean, someone who's, religiously inclined might stare out at our universe and say, it looks like it's just made for us, as well as this planet that we call Earth. How could that be possible without intelligent design? But the anthropic principle just says, well, if this universe wasn't made out for us, or this planet wasn't suitable for us, then we wouldn't be alive. The fact that we are here even talking about it is proof that that probability occurred. And then the multiverse theory makes that anthropic principle, it lends it even more credibility, because it says the laws of the universe, which appear to be sort of teetering on a knife's edge, how could that be possible? Well, we just happen to be in one of the many universes where these laws are
a very
as they
tiny
are.
fraction where the laws are such that chemistry can exist, organic chemistry, where the universe itself is big enough that, most of the solutions of the theory, and when I say the theory, I mean the combination of string theory and other things, most of them involve regions of universes, let's call them, which are far too small for you to even fit in. Right? Why don't we live in one of those, since those are most of them? Well, we can't, because they're too small for us. And that's the kind of explanation which is correct for why we live on the Earth. It might be correct for why we have 2 eyes instead of 100 eyes. It might be true many, many different properties of life. But it's not the kind of solution that most physicists would have favored, let's say 20 years ago or 25 years ago. They wanted a theory with the mathematics would explain exactly why everything is exactly the way it is. Not where the mathematics would say there are many, many possibilities, but where the mathematics would say there's only one possibility and it's exactly the kind that we live in. That seems very unlikely now.
Does this mean there are potentially infinite universes?
That's what some people would say. I have an aversion to infinity, but that's a sort of personal
aesthetic.
Yeah. So I don't know.
Yeah.
I don't know.
So there could be a universe where we're having the same interview, but I stop it halfway through and shave off one of my eyebrows.
Yeah.
Wow.
Yeah.
I've just got
right.
I've just got a couple more sort of, I guess, more general questions before we finish. The first is, I mean, a lot of this would sound, incredulous or at the very least very counterintuitive to people who aren't well versed in physics. But I suppose, I've heard you say this before, but that's really the point. We've evolved these brains that
can comprehend the unintuitive, let's say. But what did I say?
Well, you said something like, we've evolved in a world of 3 dimensions, and so we're adapted to that. But we can't visualize in our mind's eye more than 3 dimensions.
That's right. Most people, I don't know if there are any people who can visualize. By visualize, I mean, close your eyes and see it, or I think I used the word grok it, which meant deeply understand, deeply intuitively understand. No, I don't think, I can't close my eyes and visualize 7 dimensions or 12 dimensions or 10 dimensions, not at all. I also don't think that I can visualize the world of quantum mechanics in the same way. What we seem to be provided with is the ability to do a kind of abstract mathematics that lets us understand what a 12-dimensional sphere is without being able to grok it. We can write down the equations for what a 12-dimensional sphere is. We can write down the equations for how quantum mechanics works. So we seem to have this adaptable ability to be able to use abstract reasoning to understand things that we were not evolved to understand. I can tell you this. If a human being in the early parts of human existence had evolved an ability to think quantum mechanically, he probably would have been killed immediately, tripping over his own uncertain feet, or being swallowed by
By a
saber-toothed tiger. It's only because we live in a much more benign world that physicists can survive.
Yes. Well, thank God we live in, or whoever, that we live in that world.
Right.
So we can't conceptualize 5 dimensions, but we can write down X, Y, Z, W.
We invent new kinds of conceptualizations, I would say. I wouldn't say we can't conceptualize it.
We can't visualize.
We can't. I can't close my eyes. I can see a 3-dimensional cube if I close my eyes. I have learned to be able to visualize a little bit what a 4-dimensional cube is like. But can I visualize a 10-dimensional cube? No, it's just way beyond my powers of visualization. Does it matter? No, because I know how to think mathematically about what a 10-dimensional cube is.
Have you ever met anyone who's claimed that they can visualize multiple dimensions?
No, I don't think so.
Yeah.
I don't. It would not surprise me if some physicists, mathematicians, have evolved a kind of ability to be able to
like a language.
A language for it.
Yeah.
In fact, I know how to do that.
Yeah.
But no, I don't think their brains are simply equipped to be able to form images of higher dimension. So if you mean understand and visualize, you mean literally visualize. Close your eyes and see it in some sense.
Yeah, impossible.
No, right.
So we're speaking here at Stanford, where you still teach, you still come to work.
Yeah.
I'm curious, of course. I'm curious, what's it like to be, a 70-plus-year-old physicist?
Almost 80.
Almost 80. 78.
78.
Yeah.
Yeah, I'll be 78 next month.
Next month. Happy birthday.
What is it like? Well, it's always, first of all, intellectually, physically, I feel older. There's no question of it. Things hurt. I don't think my mind works any differently. It feels pretty much the same. Doing physics feels like the same thing it always did. But I often just think to myself, wow, what's going on here? I was supposed to be done by the age of 40. Physicist was always a young person's game. I used to use the word young man's game. Of course, in most of the history of physics, it was a man's game. Now it's just become a person's game, and it is. There's very many excellent women physicists, so I won't say young man's game, but it was supposed to be a young person's game, like basketball. Like athletics, your mind just became inflexible at a certain point. That was supposedly what happens. That seems to have changed. I don't know if it's changed because humans have become healthier or whatever. I don't know what the reason for it is, but I often think to myself, I'm very, very surprised that I'm still around and functioning as a physicist. So while I don't feel any different, it's a source of wonder that I'm still here.
Yeah, it's very impressive.
Yeah.
Leonard, if you could, stick around for the next 300 or 400 years,
Right.
what problem in physics would you most love to see solved?
Oh,
if there was just
that's
one.
kind of not the way it works. Each solution to a problem, each time a problem is solved, it leads to whole new classes of questions that you could not have predicted before that problem was solved. The answers to questions create new questions, and they are questions that you could not have predicted until you knew the answers to some questions. I cannot predict what the questions of physics are going to be in 500 years. Perhaps if I knew the answer to the questions which I'm interested in now, I would see further questions that I would be likely to become interested in. But right now, the questions that exist in front of me are enough. They're enough. They are definitely not understood. They have to do with the questions between quantum mechanics and gravity. Mm-hmm. And what they will lead to when they are solved, what new questions they will lead to, I cannot predict. And I don't want to try to predict.
Yeah, it would be silly to try.
Well, silly or not silly, I'd almost certainly be wrong.
Yeah, sure.
But it's not just wrong. I think the questions I would conjure up now would not be nearly as interesting as the questions which will actually arise from the solutions to the things we're doing now.
Yeah.
That's historically the way it worked. And I would expect that will continue.
Leonard, it's been a real privilege. Thanks for taking the time to speak with me.
You're welcome.
How good was that? Thank you for listening. I hope you enjoyed that as much as I did. And if you're interested in following up on some of Leonard's ideas, he has a great book called The Theoretical Minimum: What You Need to Know to Start Doing Physics, as well as a great series of lectures covering everything from classical physics through to quantum mechanics, which Stanford University released as a series of podcasts. I'll put the links to those along with everything else we discussed up on our website. And if you enjoyed this conversation, then please share it with your friends. I'd love it if you could tweet it out or share on social media and help spread the word about what we're doing. And until next week, I'm Joe Walker. Thank you for listening. Ciao.